Hi, welcome all to day one of our two-part Speak Out for Engineering Global Finals event and award ceremony. I'm Samantha Diraj, and I'm your Master of Ceremonies for today's proceedings. I'm currently the Young Member Representative for the Americas, as well as a volunteer with the institution for the past 6 years. I have a background in engineering asset management, and I currently work within the tech industry. A fun fact, I've actually of this event. What exactly is Speak Out for Engineering? Just to give you a brief overview of what exactly to expect from the competition, the Speak Out for Engineering is a competition for young engineers designed to help develop verbal and visual communication and explaining technical mechanical engineering related subjects. The competition is organized and run annually by the young members of the institution. It was established back in 1964, and the competition continues to challenge young engineers to really prove that they can communicate effectively. It is specifically concerned with verbal and visual communication in describing and explaining technical related subjects. Competitors must give an oral presentation on a mechanical engineering subject to be broken down with a presentation length of 20 minutes and a Q&A session of 10 minutes. The Speak Out for Engineering competition is now being held across the globe as our finals. The winners from each heat are invited to participate in the regional final, and the winner of the regional finals are then invited to participate at the Grand Global Final, the winner of which will be crowned the overall Sophie winner. Sophie is actually now in its 55th year. For the first time since its inception, the final is actually being held on a virtual platform. The two-part final will bring together the 2019 champions from the 8 regions: the Americas, Europe, Southeast Asia, Northeast Asia, Middle East and Africa, Southern Asia, Oceania, UK and Ireland, to battle it out one last time to see who will be crowned the 2019 overall Sophie winner. A 20-minute pre-recorded video presentation from each of the finalists will be streamed live today, after which each competitor will participate in a live interactive Q&A session. On day 2 of the competition tomorrow, after a short break for the judges' deliberations, there would be an award ceremony. The ceremony will be conducted by the president, Terry Spall, and prizes funded by the institution's trustee board awards committee will be awarded to the winner and the runner-up. The first prize will be £300 and the second prize £200. Today, we're eager to see presentations from the Middle East and Africa. We have Muhammad Haseeb Kazim, Europe, Oktay Güçlü, the Americas, Jeremy Lalchand, and the UK, Callum. Tomorrow, we shall see presentations from the Oceania region, Geraldo Tegush, Northeast Asia, Selena Wipheya, Southeast Asia, Christine Tan Shimin, and South Asia, Fahim Islam Anik. Please reminded that there is the agenda and it can be found on the webpage where you registered. Also, I would like to make mention as well that this year we have an excellent panel of judges who will be with us for both days. They'll be looking for the structure and content of the presentation, the quality and preparation, how the contestants handle the questions, and their presentation style, for example. A reminder, please note that 90% of the marks will be awarded for the presentation and only 10% will be awarded for the technical content. This actually ensures that while all presentations must have a mechanical engineering content in its broadest sense, a topic concerning comparatively low technology has an equal chance to be successful as one which is technologically very complex. Now that I've given you a brief overview of what to expect for the Sophie competition, I would now like to move over to our judges, and I would like to introduce our judges for the competitions today. Our first judge is Terry Spall, and he will be our head judge and award presenter. Please, Terry, I would like you to share a few words with us today on your expectations for the competition. Thank you.
Okay, thank you, Sam, for the introduction. I am actually the 135th president of the Institution of Mechanical Engineers. Our first one was back in 1847, and that was George Stephenson, who gave the world the locomotive. And while his achievements go well beyond my own, but my presidency comes after a 40-year career in the automotive industry. And I can't really stress enough the importance of engineers having the ability to present and communicate effectively. It is a real skill, and it may be one of the most useful skills that you'll develop through your career, and it can have a very positive impact on your career as well. And I'm speaking from experience because I too was a Sophie competitor. I was in the competition in 1985. And back in those days, it wasn't called Speak Out for Engineering. It was called the Queen's Silver Jubilee competition, but it was exactly the same. And I still remember my heart racing at the prospect of making the presentation. And these days, after 40 years of making presentations, it doesn't even miss a beat. So you get better and better as you go on. All you need to do is keep practicing and keep doing it. And it's a real skill. And for me, it's helped me to make that journey from apprentice to board director and now president of the institution. So I'm looking forward to working with my fellow judges today and tomorrow, hearing some really, really great presentations. And I wish all the candidates the very best of luck.
Thank you very much, Terry. Our second judge, director, member of operations of the IMechE, Joanna Horton.
Thank you, Sam. It's really great to be here today, and I'm really looking forward to this year's virtual Sophie competition. As Sam said, my name is Joanna Horton, and I work for the institution as a director of member operations. So I'm very engaged with engineers, but I'm not an engineer myself. So I'll be very interested to see how you translate some of these engineering projects into for the layman, so to speak. I'm very much looking forward to judging, but I'm also very interested in how you find this competition. This is one of the many opportunities we provide for young engineers to develop their skill sets, both in engineering, but also in those sort of leadership and communication skills. So we very much, hopefully you find this very rewarding. And if you do, I would urge you to stay engaged with the organisation and get involved. So as Terry said, good luck to everyone. And I'm really looking forward to the next couple of days. Thank you.
Thank you, Joanna. I will now introduce our third judge, an engineering policy advisor, Carly Nettleford. Hi, Carly.
Hi, thank you very much for introducing me and having me here today. As Sam said, I am Carly Nettleford, Engineering Policy Officer. I also work for the IMechE, and I joined earlier this year. So this is the first time I'm ever getting to do anything like this, so it's really exciting. I'm also an engineer. I have a lot of experience in the field. I began as an apprentice and worked my way up doing a lot of hands-on jobs. So I've done similar things to what you guys are doing. I've worked on loads of different projects, and I'm really, really excited to see what you guys can bring. Hopefully you'll have a lot of good technical content, and I wish everybody the best of luck.
Thank you, Carly. And our final judge and Toastmaster today, Stephen Francis. Hi, Stephen.
Hello, I'm Stephen. Can you hear me?
Yes, Stephen, we can hear you. Yes.
Okay.
Thank you.
I'm from Malaysia. I'm not an engineer, but I have been with the bank for 28 years. I was in HSBC, Malaysia, for a long time. But now I have been in Toastmasters for the last 26 years. And in Toastmasters, there are many presentations that we go through. I'm very happy to be participating today to see how you fare, and I hope I can add some value as well. Thank you so much.
Thank you, Stephen. And a warm welcome to our judging panel. We're super excited to have you guys for the next 2 days. So thank you so much. Now let's begin the competition. Is everyone excited? I know I sure am. I do look forward to seeing these presentations. So now I would like to introduce our first competitor for the Speaker for Engineering 2019 finals. Our first competitor is Muhammad Haseeb Kazim, and he will be representing the Middle East and Africa. Just a brief overview of Haseeb. Haseeb is actually a graduate with a BE in Mechanical Engineering from the National University of Sciences and Technology, with electives such as robotics, mechatronics, and CFD. And he was actually awarded the Rector's Gold Medal for the best final year project for design, development, and testing for transformer processes. So today we'll be seeing Haseeb's presentation, which is titled the Kadam Knee Joint. So I would now welcome Haseeb's presentation.
Good morning. I'm Mohammad Haseeb, and today I'm presenting the Kadam knee joint. In the Urdu language, Kadam means taking a step forward. Kadam is Pakistan's first indigenously developed polycentric knee joint. Our mission is giving small steps to big aspirations. Firstly, I would like to acknowledge the role of these organizations in the development of the device. We owe our progress to their help and support. Kadam was developed as my final year project at the NUST School of Mechanical Engineering, Pakistan's highest ranked university. The team comprises of these 4 members. Firstly, I will focus on problem identification based on these factors, and then on the proposed solution. Let's start with a short video to introduce above-knee amputation.
13-year-old Ali Shah's life took a dramatic turn late 2014 as he was walking to school in one of Pakistan's tribal districts. He stepped on an IED, losing half of his right hand as well as his left leg.
There are more than 50,000 above-knee amputees like Ali in Pakistan who have lost their limbs to accidents, disease, or terrorism. The majority of such amputees don't have access to prostheses because these are unavailable and quite expensive. Knee amputation is a physically and mentally traumatic event. Many amputees face a social stigma and face hurdles in their education and employment. We have met several amputees and doctors, all of whom stressed the need of an affordable prosthetic knee. This dire need has inspired and motivated us to develop Kadam. Let's see the basics of human gait. The human gait cycle has 2 distinct phases, stance and swing. The stance phase begins with heel strike and ends with toe off. Now swing begins and the cycle repeats. Notice the key role of the knee joint in transferring power from the leg muscles to the foot for movement. The knee is the most complex joint in the human body and is critical for walking and stability. Injuries to the ACL or PCL are often career-ending for amputees. So imagine the effect of losing the entire knee. Broadly speaking, leg amputation is categorized as either above the knee or below the knee. Above-knee prostheses are much more complex and expensive because the knee joint has been completely amputated, whereas below-knee amputation is much easier to remedy because the knee is still present and fulfilling its natural function. Above-knee amputation has several physical and psychiatric effects, ranging from loss of mobility to phantom limb phenomena. This is why it is necessary to provide treatment as soon as possible. Statistics from the World Health Organization alarmingly indicate that up to 95% of amputees in developing countries don't receive any prosthetic device. Large-scale surveys in India have shown that the amputees expect the prosthesis to have certain region-based characteristics, such as the ability to sit cross-legged and extra durability for less maintenance cost, especially in the climate of the subcontinent. We collaborated with these artificial limb centers, AFIRM and Fauji Foundation Hospital. We collaborated to see the existing facilities and devices and to gauge the requirements of Pakistani amputees. Both institutions expressed the need for affordable, high-performance prostheses. Let's have a look at the technologies which are commercially available and also those under research. The most basic design comprises of a fixed leg made of composite materials such as wood or plastic. This rigid leg is quite difficult to use since the knee doesn't flex during walking, and thus the amputee has to exert a lot of energy to walk. This leg has the same functionality as this 2,000-year-old wooden leg uncovered in China. Unfortunately, this ancient design is still the only option for most amputees in developing countries. These are the modern commercial products in order of increasing cost and functionality. The basic devices are passive, which means that they do not have an external power source, and the advanced ones are active and embedded with advanced control systems. Even the device on the lower end of the price spectrum is unaffordable for the vast majority of amputees in developing countries. There has been extensive research on prosthetic knees in the last 2 decades, focusing either on providing low-cost passive devices or high-performance active solutions. These devices present a range of innovative solutions and are in different stages of testing and development. Let's compare 2 devices on opposite ends of the price spectrum. Amputee 1 is using a microprocessor control device, representing the cutting edge of technology. The manufacturer, Autobok, is the leading company for prosthetics in the world. Amputee 2, on the other hand, is using a very basic spring-powered device made by DREV. As we can see, Amputee 1 can change his speed from slow to fast and walk with confidence. Amputee 2, on the other hand, has to consciously match the speed of his healthy leg with the prosthetic limb, and is thus visibly uncomfortable. He has to look down to match the speeds. The confidence and comfort of the Autobok device has a price. It is 50 times more expensive. To overcome the significant barriers to entry we faced, Kazmi has to innovate in materials manufacturing and design. Most prostheses are made of stainless steel, titanium, which are difficult to machine and quite expensive. 7 Series aluminium provides the best financial bargain amongst the available materials. The device has complex features which require a 4-axis CNC, which is not available. 3D metal printing is a new manufacturing process, and this is also not available in Pakistan. Therefore, investment casting was used for the first prototype, and for the second prototype we used 3-axis CNC machines with jigs and fixtures to make the complex 3D features. Kazmi has been designed to function with much fewer parts than a comparable polycentric knee made by Autobok. Fewer parts will simplify manufacturing and maintenance. Kadam comes with two modes, passive and semi-active. The semi-active module has intelligent control and uses a linear actuator to increase performance. Whereas the passive module doesn't need a motor to work. It is designed to be interchangeable between the two modes, and so it may satisfy a range of users with different needs. The design and development phase spans from mathematical modeling up to prototyping. The analysis is based on the geometrical and mass properties of an average adult male. And the mathematical model was based on two cases, stance phase and swing phase. And Maple, which contain several partial differential equations. The full solution is around 80 pages long. Input data for motion analysis was taken from the dynamics of human gait by Vaughan. This is the normal foot trajectory during walking that we aim to emulate in our model and device. And motion analysis was performed iteratively on Adam's software, and this is the foot path lines and the motion curves, and you can see that these match with the ideal trajectory seen in this figure. The device 3D model was made in SolidWorks, and finite element analysis was performed in ANSYS based on the worst case loading scenarios. The maximum stresses obtained are used to establish the factor of safety of the device and to estimate its fatigue life. After completion of analysis, we moved towards prototyping. Precision 3D printed parts were used as patterns for investment casting. This is the casting process, and these are the cast parts. These were cleaned and machined to make and then assembled to make the first prototype. All the cast parts are made of carbon steel, but some links were replaced by CNC machined 7 series aluminum to reduce the weight. Replacing the links with a lighter metal reduced the overall weight of the assembly while maintaining the same functionality. This is the second prototype. It is completely made with CNC machining with the addition of tapered bushings as a design improvement. The bushings can be replaced when they wear out, so the main body of the device is not damaged. The prototyping stage is followed by testing and evaluation. This is the standard assembly that an above-knee amputee uses. The amputee inserts their residual limb into this socket. We inserted the pyramid connector into a standard tube connector, and the prototype fits properly. Therefore, the device is compatible with the universal standard connectors. A special socket for testing on healthy subjects was developed in AFRM. As you can see, this test subject has both his legs, and still he can place his leg into this special socket for testing. These are the dimensions for the cast, and this is the casting process. And these are the testing facilities used in AFIRM, such as the support rails and the pressure pad. The amputee stands on this pad for alignment and adjustment of the device according to their weight and dimensions. As you can see, the amputee is using the special socket here. They have strapped their healthy leg into the socket. And we have used two setups for testing, one for the passive mode and one for the semi-active mode. The semi-active module was tested on a treadmill for convenient measurements of speed, and a maximum speed of 4.2 kilometers per hour was achieved. Mr. Ahmed lost his limb in a shooting accident 20 years ago. We were lucky to find him, since there are very few amputees who use knee joints which have the compatible pyramid connectors. Mr. Ahmed is an ideal test subject since he's 6 feet tall and weighs 92 kg, which is the upper design limit of the device. The device did not fail during extensive testing, and this validates the results of the design, modeling, and stress analysis. These are the resulting graphs of knee angle versus time obtained using an IMU sensor placed on the knee. Mr. Ahmed was then using an Autobok single-axis knee joint, and Kazmi has quite a similar curve. In fact, the curve is smoother in the stance phase. Mr. Ahmed gave an interview. Let's see the part where he discusses his experience.
मेरे पे ट्राई की है जो बना के आपकी अपनी जो है वो उसमें और जो ऑटोबॉक की उसमें इतना ज़्यादा फर्क नहीं है, सिर्फ ये फर्क है कि मुझे हल्का सा थोड़ा सा जोर लगाना पड़ता है चलने में, बाकी तकरीबन वैसे ही है, ठीक है। और वेट का भी इतना इशू नहीं है, वेट भी तकरीबन उसका थोड़ा सा हल्का सा 19-20 का फर्क है। और मजीद ये है कि इसमें आवाज़ जाहिर बात है उसकी बिल्कुल साउंड है, वो तो मल्टीनेशनल कंपनियां एयरपोर्ट पे लगाया हुआ है, लेकिन आपने बहुत ही इसमें ये है कि एक तो सबसे अच्छी बात ये है कि
His feedback is very useful and encouraging, and we will continue to improve the device and test with him in the future. Now that a minimum viable product has been developed, there are some important considerations for costing and production. Firstly, we need to survey and test a larger sample of amputees, at least 20 to 50 more. The device needs medical accreditation from local and foreign bodies. The production method can be machining or die casting, depending on the quantity and initial capital expenditure. For producing amounts in the hundreds, CNC machining is cost effective, and for thousands of parts, metal die casting is the way to go. A basic and conservative model based on inputs from industry experts shows that within the first year of operation, up to 500 devices can be produced and generating a revenue of up to $100,000. The project has achieved several milestones so far. I presented the device to the Federal Minister of Science and Technology on national television. Our team won the gold medal for best academic project amongst 36 teams. We were selected for incubation at the National Incubation Center out of 1,200 plus applicants, and we have a patent pending for the device in Pakistan IPO. The future work comprises of more testing and surveys, involving specialists such as doctors and biomedical engineers, and making improvements based on user feedback. In conclusion, let me sum up Qadam's mission. For the 50,000 plus amputees in Pakistan, we aim to provide a solution which has high performance, low cost, and is manufactured indigenously. Thank you very much for your attention. I look forward to answering any questions that you might have.
Thank you very much for your presentation, Muhammad Haseeb Kazim. We now open the forum to accept questions from the member of our audience as well as our judges. Very insightful presentation, and thank you again for taking the time to deliver. So our Q&A session will now commence. We would have questions from our judges as well as questions from our audience, which I will read. So please, judges.
Okay, if I can go first, Samantha. So, Mohammed, congratulations on a really excellent project. You've already had some success with it, with the awards that you've already won. So many congratulations on that. It's very clear to see the application of it and to see the constraints that you try to work within. I just want to ask a question now about how far this design can be developed further. So, when it comes down to the actual user of the device, and I'm thinking now about how it feels to use. So, have you looked at the inertial characteristics, see if you can optimize those to make it feel more like a real limb? And have you to consider things like damping in it to give it the right sort of motion?
So the most important thing for the comfort of the amputee is the exact area in which the prosthesis meets his amputated limb, and that is the socket. So a lot of research is being done in that part, in which the amputee inserts his limb. So the prosthesis is actually not connected directly to his amputated limb, and there's a bit of cushioning over there. So what they want to achieve is to exactly meet the profile of the amputated limb so that the stresses are minimized and the amputee can use the device comfortably. So we will collaborate with the limb centers in Pakistan on working on that. And for the inertial properties, as was shown in the presentation, we are trying to reduce the weight of the device as much as possible to bring it close to the natural human knee. But that is difficult because the materials which we are using are metals, are heavier than bone. But we're trying to optimize that by using lightweight metals like 7 steel or titanium.
Okay, thanks, Mohammed. Did you also consider the use of composites or plastic?
We went to an aircraft manufacturing facility which was using carbon fiber, but the issue was that they were the manufacturing facility was solely for aircraft. It wasn't meant for really small precision engineering. So that was another manufacturing limitation. So we had to go with CNC machining and casting.
Thank you.
But definitely we will consider composites. Yeah, sorry.
Mohammed, this is Jo. Thank you very much for a very informative presentation. And also, I think it really demonstrates how engineers can change the world and support people. My question was around, you mentioned the use of aluminium, and you looked at a number of different metals, mainly from a financial point of view. But I wanted to understand if there was any negatives or disadvantages from using that substance.
Yes, definitely. In terms of engineering, the challenge with stainless steels or titanium is that it's very difficult to machine on conventional lathes or milling machines. So not only would that add to the initial material cost, it would add to the machining cost, time, expertise required, and even the tooling is different for those metals. So aluminium 7 series gives us the necessary strength and fatigue life, but it is also much easier to machine compared to stainless steels or titanium. So those were also the other factors which we had to consider.
And how long would you expect the product to last?
Based on the stress analysis on ANSYS software, it's rated for more than 100,000 cycles. So it could probably work depending on the usage of the amputee. It depends if he's a very active user, he or she, or if they're less active. So even for an active user, it might last 2 to 3 years before it needs maintenance and replacement of parts. Even then, it won't need complete replacement. Only the worn out parts, the bushings or the points where the contact and rubbing occurs, those will be replaced. So it's not going to be a very big cost.
Thank you.
Welcome.
Hi, Mohammed. Well done. That was very good, really informative, nice, clear and concise, and good technical information. I have a quick question. You included a video of a gentleman demonstrating using the limb, and he was around 94 kilos. So, do you have an idea of the maximum weight capacity that the limb can use?
Yes, definitely. That was the purpose of doing the stress analysis and FE in ANSYS. First, he made the 3D model in SolidWorks software based on a lot of iterations. And then we carried out a static stress analysis of the worst case loading scenario, which was around 110 kg. But that was the more than the upper at around 80 to 90 kg. So there's always a factor of safety in any engineering device which is made. And our factor of safety was basically 1.3. If the factor of safety was would be too high, the device would be really heavy. So this is a compromise which we had to make. And on a 90 kg amputee, on 90 kg patient, then it's definitely going to work on every level which is around 70 or 60 to 70 for the Pakistani male.
Okay, thank you very much.
Thank you.
Welcome.
Okay. Judge Stephen?
Congrats. I don't have a question. I have actually, it was very technical. Thank you.
Okay. Thank you very much to our judges for your questions. Again, we encourage the audience to please ask any questions you may have. Haseeb, we have a question from the audience right now. What were some of the
Yeah, sure.
obstacles which you came across when completing this project?
The main obstacle was basically the really tight deadlines. And the other was the lack of advanced manufacturing facilities in Pakistan. So although we could access the raw material, we didn't really have the machining facilities to really work on those. And secondly, because this was my final year project in university, we only had 1 year to go from nothing just to a finished device, a prototype, and testing it on an actual patient. So the 1 year deadline, it really it was challenging, but we really made a Gantt what was important for us. We divided different phases, as I mentioned in the presentation: the design, the modeling, the stress analysis, the first prototype, the second prototype, and finally we are now even going to the next stage of bringing it to the market and involving more experts. So I hope that answers your question.
No problem. So thank you. Thank you very much. We actually have another question from our audience, which is, what type of investment is required for implementation?
In terms of monetary investment, we don't really have an issue. There's a lot of donors who'd be willing to pour cash into this. And we were a national incubation center in Pakistan. We were chosen out of 1,200 teams, and we also have the support of our university professor, who's the head of artificial intelligence and robotics department in our university. And also for the whole country, there's a center, and he's the head of that. So the main issue is actually the expertise. In Pakistan, we don't really have any prosthetics manufacturing company. All of them are imported from abroad. So that's the main challenge. We really need experts in biomedical engineering and doctors who deal with prosthetic patients. And we're trying to meet such people, but it's really difficult because we don't really have that kind of industry here. So hopefully we can meet somebody from abroad or collaborate with them in this project as well.
Okay, no problem. Well, I would like to thank again, Haseeb. Thank you very much for submitting your video, and thank you for the Q&A session. To our judges, thank you for your questions, and to our audience, thank you again. That was contestant
Thank you
number
everyone
1.
yes. I would like to
Mohammed
thank the
Asif
judges for
No problem. On his presentation entitled The Kadam Knee Joint. I would now like to move forward with our second presenter today, and this would be our presenter who is representing Europe. We have Oktay Güçlü. Oktay is a mechanical engineer from the Netherlands, and he holds a bachelor's degree in mechanical engineering. He has been an IMechE member for 2 years and has recently joined the Royal Netherlands Society of Engineers. Today, we will be viewing Oktay's presentation, Preventing Antibiotics Misuse with HTM Sensor Technology.
Of Speak Out for Engineering with a presentation entitled Preventing Antibiotic Misuse with HTM Sensor Technology. Suppose we are living in a world without antibiotics, and you just cut your finger from a sheet of paper. Then there is a good chance that you could die from this paper cut due to an infection. Luckily, in 1928, Alexander Fleming discovered penicillin, which is a group of antibiotics, and changed the way how we treat bacterial infections. We cannot imagine a world anymore without antibiotics for the treatment of infections. But what if I tell you that we may head back to a time before antibiotics? Before I tell you why, I want to share a personal story of my mother. When my mother was in her early 20s, she was often sick during winter seasons, where she frequently visited the general practitioner. And after almost every visit at the general practitioner, she received antibiotic prescription for her treatment. So, she used loads of antibiotics for many years. Till the moment she was suddenly diagnosed with colitis and changed her life forever. So colitis is a chronic inflammatory disease of the large intestine. And in many cases, it occurs after taking excessively use of antibiotics. As a colitis patient, she frequently experienced abdominal pain, fatigue, fever, diarrhea, cramping, and the list goes on. Unfortunately, there is no cure for my mother. The inflammation can only be kept stable over time by using heavy medication frequently, which of course makes her also very weak during the day. And this all could be avoided by reducing unnecessary and improper use of antibiotics. Did you know that 1 in 3 of all antibiotic prescriptions are unreasonable? Which is a lot if you ask me. So there is a good chance that my mother received antibiotic prescription while she probably had the flu, which is completely understandable if you're sick during the winter season. And as we know, antibiotic is not effective for the treatment of the flu, which is caused by a virus. Antibiotic can be only reasonable use for some type of bacterial infections and not for viruses. So this problem is better known as antibiotic misuse, and it is a serious problem in our society. The main danger of antibiotic misuse is the development of antimicrobial resistance, in which certain bacteria can become resistant against antibiotics, which eventually could limit the effective treatment of bacterial infections. According to the World Health Organization, antimicrobial resistance is placed within the top 10 for global threat. And what really scares me is that if antimicrobial resistance continues to increase from current levels, it is estimated that by 2050, 10 million people would die every year due to lack of available treatment. So what is this cause of antibiotic misuse? Imagine a sick person visits the doctor's office, and the doctor needs to find out whether the patient has a bacterial infection or a viral infection. In order to find an answer to this question, laboratory testing is needed, as 70% of all clinical decisions are based on laboratory testing, as it provides reliable test results. So, the doctor needs to collect the sample from the patient, which could be, for example, urine or blood, and send the sample to the laboratory for testing. When the testing is done, the lab technician will send the test results back to the doctor's office. One major drawback of this type of testing is that it can be extremely time-consuming, and an actually ill patient cannot wait for days to get the right treatment. So, empirical decision-making will often result in the use of broad-spectrum antibiotics. And that is exactly one of the major drivers of this antibiotic misuse problem. So, what if we can find ways to take this type of testing out of this laboratory environment and bring it to the immediate care and living environment of the patient to provide quick medical diagnostics tests, thus providing quick and appropriate treatment? And that is exactly what point-of-care testing is all about. So, point-of-care diagnostic devices are used to obtain fast and reliable test results while with the patient or close to the patient. They are mostly used in doctors' offices or even in patients' homes. So, by implementing these rapid diagnostic technologies, particularly at the point of care, would assist clinicians in determining whether a patient requires antibiotics without delaying the start of treatment. As mentioned earlier, my mom was a victim of antibiotic misuse, which resulted in an incurable chronic disease. I wanted to help my mother somehow, but I felt hopeless as it was simply too late. But deep in my heart, I knew I wanted to be part in this fight against antibiotic misuse, as it is a serious global problem. So during my engineer's degree, I worked on a research project named SurfScan, and where we developed a new sensor in the fight against antibiotic misuse. My name is Oktay Güçlü, and I'm a mechanical engineer from the Netherlands. As a young engineer, I'm committed to inspire, connect, and support young engineers from all over the world. My number one goal in life is to make an impact to improve the world by developing new technologies and push the boundaries of engineering. So, during this research project named SurfScan, we developed a novel sensor readout technology, in which we called the heat transfer method, HTM, for detecting cells on a fast, sensitive, and low-cost way. This technology can also be used in point-of-care devices. On the right, you can see a picture of one of the first prototypes of this sensor. And according to the dimension, it is indeed a really compact design, which can be placed easily in the doctor's office, for example. So this is how the sensor looks like, which consists out of several important components. So in the top section, we have the fluid chamber, in which we apply the sample from the patient, for example, urine or blood, through the inlets and outlets. In the bottom section, we have a heating element, which produces a certain amount of heat and is directly attached onto a copper block to transfer this heat to the fluid chamber. In between the top section and the bottom section, there is a surface imprinted polymer receptor, or SIP receptor, which is placed on an aluminium plate. So a SIP receptor is basically a synthetic receptor which can bind to specific cells. So if we zoom in on this SIP receptor, as shown in this picture, which is made by an electron microscope, we can see these micro cavities on the surface layer of this polymer. And so these cavities have the exact same geometry and dimension of the target cells. So these target cells can bind like a key lock principle in these cavities. So how are these CYP receptors made? Well, first we isolate the target cells and we place them on a silicon stamp. Next, by spin coating, the excess buffer solution will be removed and the target cell will form a nice monolayer on the stamp. Next, we stamp the target cells in the polymer layer, and after removal of the stamp and target cells, these microcavities are created in the polymer, in which we have our own CYP receptor. During our research, we mainly focused on diagnosing urinary tract infection, UTI, as it is one of the most common bacterial infections worldwide. UTI ranked also as the #1 infection that leads to an antibiotic prescription after a physician visit. According to previous research, we also know that E. coli bacteria is responsible for 85% of all the UTI cases. So in our research, we use these E. coli bacteria as our target cells, basically. So how does this technology work? So here we have a simplified illustration of our sensor. So on the top we have our inlet and outlet in which the fluid can enter and exit the fluid chamber. In the bottom of the fluid chamber we have our CYP receptor, which is placed on an aluminium plate. And this aluminium plate is directly attached onto a copper block, which will be heated up by the heating elements and will be held constant at a temperature of 37 degrees Celsius. So in order to perform the diagnosis, we have to perform 2 temperature measurements by using 2 fluids. It sounds simple, but it is really simple. So buckle up, because now I'm going to explain you how this technology works. So first we apply a water-based salt solution in the fluid chamber, in which we call PBS, and we close the inlet and outlet with an active valve system. Next, we are going to measure the temperature at 2 positions. So first, we are going to measure the temperature T1 in the copper block, and we are going to measure the temperature T2 in the fluid chamber, which of course will gradually increase in temperature due to heat transfer. So now we start with our first temperature measurement. As the PBS do not contain these target cells, these microcavities on the surface layer of the CYP receptor will form a preferential heat channel, as shown in this animation. After the first temperature measurement is done, which takes approximately 5 minutes, we can calculate the terminal resistance through the CYP receptor with the following equation, which is equal to the temperature T1 in the copper block minus the temperature T2 in the fluid chamber divided by the power of the heating element. So after calculating the terminal resistance of the first temperature measurements, we open the valves and we flush away the PBS. And now we apply the urine from the patient in the fluid chamber, and we close the inlet and outlet with the active valve system. And now, in case of presence of these E. coli bacteria in the urine, these E. coli bacteria can bind on the CYP receptor as shown in this animation. After that, we open the valves, we flush away the urine with a fixed flow rate to ensure that these E. coli bacteria are not flushed away from the CYP receptor, as shown here. And now, again, we apply the PBS in the fluid chamber, we close the inlet and outlet valve again, and now we are starting with our second temperature measurement. And here's the interesting part. Because these E. coli bacteria are binded on the CYP receptor, this will increase in the thermal resistance through the CYP receptor, because now the heat is forced to transfer over the thicker non-imprinted regions. And because this increase in thermal resistance will eventually decrease the temperature T2 in the fluid chamber. And now, after the second temperature measurement is done, we can again calculate the thermal resistance for the second measurement. And differences in the first and second measurements gives an indication about the amount of E. coli bacteria in the urine in order to diagnose whether the patient has the infection or not. As engineers, we always look for further enhancements, such as improving the sensitivity of our sensor. By improving the sensitivity of the sensor, we can increase the overall reliability of our test results. So in order to improve the sensitivity, we have to create a nice homogeneous heat flow in the axial direction in the fluid chamber, as shown in the left animation. And so in order to achieve this, we have to overcome and suppress convection currents in the fluid chamber, as shown in the right animation. So in thermodynamics, convection is a form of heat transfer which occurs only in fluids, such as gas or liquids. So how does convection really work? Well, explaining thermodynamics can be really boring. And that's why I use Justin Bieber's face as these fluid particles. Well, because who doesn't like Justin Bieber, right? So we have all these particles in this closed room. And they all have roughly the same energy, which we can see because they all move at the same speed. Now suppose we put fire in the room. And so these particles close to the fire start to gain energy from it. And so they move faster. And because they are moving faster, they spread out. So that bit of fluid becomes less dense now. And because it's less dense, it rises. And of course, they cannot leave nothing behind. So these cooler fluids will move in and replace them. And now these particles are close to the fire, so they start to gain energy from it and move faster. And because they are moving faster, they become less dense. And because they are less dense, they rise. And this will happen over and over again, forming a heat convection current, as shown here. In order to model the temperature profile in the fluid chamber to analyze the convection effect, we as mechanical engineers like to perform computer simulations. So in the first simulation, we took an aspect ratio of 0.35, which is defined as the ratio of the height of the fluid chamber and the diameter of the fluid chamber. The temperature underneath the fluid chamber is always held constant at 37 degrees Celsius. So, according to the first simulation, we can see these temperature profiles, which is not truly homogeneous in the axial direction. So, in order to further suppress and diminish convection current in the fluid chamber, we can change the dimension of the fluid chamber by adjusting the height and thereby decreasing the aspect ratio. So, in the second simulation, we decrease the aspect ratio to 0.25 by adjusting the height. And now, according to the second simulation, we can observe a more homogeneous heat flow in the axial direction in the fluid chamber, which is suitable, and thereby, by decreasing the aspect ratio, we can suppress convection effect in the fluid chamber. Back to my first question. Are we really heading back to a time before antibiotics? By improper and unreasonable use of antibiotics, as we are continuing to do right now, yes, we're heading back to a time where you literally can die from a paper cut. But engineers and scientists from all over the world are working hard towards new technologies, such as the heat transfer method for preventing antibiotic misuse. Now that I've come to the end of my presentation, I want to share some tips what you can do. Tip number 1, only use antibiotics when prescribed by a certified health professional. Tip number 2, always take the full prescription, even if you feel better. 3, Tip 3, never use leftover antibiotics. 4, Tip 5, never use antibiotics when prescribed by a certified health professional. Tip 6, always take the full prescription, even if you feel better. Tip 7, never use leftover antibiotics. Tip 8, never use antibiotics when prescribed by a certified health professional. Tip 9, And tip 4, never share antibiotics with others. Thank you for watching.
Thank you very much, Oktay, for that presentation. Well done. Thank you so much again. Before we begin our Q&A session, I would like to encourage the audience to please send through your questions as we proceed throughout the presentations. Thank you so much. Oktay's presentation again, preventing antibiotics misuse with HTM sensor technology. Hi, Oktay. I will now open the Q&A session with our judges.
Thank you.
Okay, thank you,
Oktay.
Terry Spall here. So, Oktay, if I might, I've got 2 questions for you here. The first one really is about the type of sensor technology. So you very early on decided on a particular type of technology to use for your sensor. So I want to ask, did you consider other types of sensor to achieve the same result, and what made you choose the one that you did choose? And secondly, what would actually register as a positive test? So when you do the test and you put the sample in, what's the threshold for it being a positive test? And did you actually do any comparisons with real infections to see how effective it was?
Well, Terry, thank you for your question. That's a really good 2 questions. Let me start with the second question first, because the second question can be answered easier and quicker. So basically, according to previous research, we know that a patient has the urinary tract infection when there are approximately more than 100,000 colony-forming units per milliliter of urine. And we also found out that so when there are more CFU per milliliter of E. coli bacteria in the urine, the thermal resistance will increase. Okay, and so in our research, we saw that at 100,000 CFU per milliliter, that value is basically associated with a certain degree amount of thermal resistance. So we know that when the thermal resistance surpasses a certain threshold, we can confidently say that the patient has the infection, basically. The first question I didn't really understand well due to the bad connection, I think. Could you please repeat the first question?
Yes, of course, Hector, no problem. I was just really saying about the sensor technology that you've created there. I just wanted to ask the question, did you consider other types of sensor to achieve the same end result, and what made you decide this particular sensor technology?
Well, indeed, that's a really good question, actually. So basically, we developed a new sensor readout technology. And the reason why we focus on this new type of readout technology is basically that the current technology in the market is based on laboratory testing, which is extremely time consuming. And that's the whole problem with this antibiotic misuse. You want to have fast, reliable, and cheap tests available in the market. So basically, with this new sensor readout technology, which is based on the heat transfer method, the test can be performed like within 10 minutes on an extremely low cost and sensitive way, which makes it really appealing, actually, compared to the other products in the market. And as with the whole idea of this sensor, we want to achieve the standards of point-of-care testings. Well, point-of-care testing is not new, right? Like the most simplest point-of-care test device you can imagine at this moment is basically a pregnancy test, right? A pregnancy test is basically a point-of-care device in which you can use it by yourself at your home. And so basically with this new type of sensor technology, we want to bring this type of testing really close to the patient. Even in patients' homes. So we want to make it really easy to use on an extremely low cost and sensitive way. So that's basically the whole idea. Yeah, thank you.
Hi, Oktay, nice to meet you, and thank you very much for a great presentation. It's such a big issue around the world at the moment. I've got quite a few questions, but I'll limit them to only 2, if you may. First one is I'd be interested to know more about the costing. You've mentioned about the low cost, but what does that actually look like in practice? Yeah.
And
also just linking to the home testing, which I'd be really interested, especially in the world today when it's very difficult to get to a doctor. Do you see this being applied by a non-professional to work out what is going on with their body, perhaps, or do you see this always being linked to the medical practitioner?
Let me start with the second question, because I really like the second question, actually. So basically, the idea behind our research is that we wanted to design this type of sensor so it's really easy to use. Because at the current technologies, lab technicians, which are trained to use these types of technologies, but we want to change that. We want to have, for example, a general practitioner without lab technician skills, and even patients itself can use it. It's really easy interface and easy tasks in order to conduct the tests. So we're really focusing on getting rid of the lab technicians in a laboratory environment, and so that actually a simple general practitioner or a nurse or even yourself can use it in the future. And that's the whole idea, indeed. Could you please repeat the first question?
It was just, I was quite interested that you mentioned about the costings. I just wondered if you could explain a little bit about those costings and, how much it costs potentially for production.
Yes, it's actually really cheap. For example, the most important component, which is the CYP receptor, right, where these bacteria can bind on the polymer layer, in which we are calculating the thermal resistance through the CYP receptor, and the CYP receptor is basically around 0.005 cents. When we talk about mass production, of course. And I also explained really clearly how these CYP receptors are made. So the CYP receptor is really cheap, which is also one of the most important components. But of course, there are also some little hardware components, such as the which is quite expensive in comparison to other parts, which is the thermocouples, because we are using thermocouples to measure temperature, right? We are measuring two temperatures in order to conduct the test. And so these are the, well, bit more expensive parts compared to the other ones. So in general speaking, the product should be around, when we say roughly 100 euros approximately, when we talk about mass production, of course.
Thank you.
Yes.
I only had one question about the sensors, but your answers have been so thorough that you've given me the answer already. So I just wanted to say congratulations. That was a really good presentation. It was very thorough, and I liked your use of your personal use involving your mum and also Justin Bieber. So well done. Very good.
Thanks. Okay. In fact, many of the questions that I wanted to ask has already been asked, but I just want to know, how long has your research been on this project?
Well, I've been active on this research project for 6 months during my last year in engineering school. I'm now graduated. I'm now working full-time as an engineer at a different company and also at a different industry. But as I mentioned earlier, I'm a really driven and enthusiastic engineer. I like to work on many problems. It doesn't matter in which industry. And for me, it was also really interesting to work in the medical field industry as an engineer, finding solutions on these really big problems. And currently, it's really interesting also because now there is a startup, a company, which took this research in the laboratory, this whole heat transfer method, and they're now a startup company with a CEO and some couple of employees based in the Netherlands also. And they're really trying to get this on the market within 2 years, which is really interesting because, when it's in the market in 2 years, I can probably say, like, I really worked on that project when I was a student. And I think I'm also really proud of that also, of that part. So maybe in 2 years, you will see it in the market.
Thank you. Congrats.
Thank you.
Thank you, Oktay, and thank you to our judges. Oktay, we have a couple questions from the audience. So,
yes.
Looking at your design of the prototype, there seems to be chances of contamination of sample. contamination can cause incorrect readings. Is there any mechanism in procedure in place to prevent this? And there's a follow-up question to that. My second question would be, is this device only applicable to detect E. coli? What other bacteria can it detect?
They're really great questions. Thank you for that one. So the first question is really easy to answer because this whole concept idea of this sensor is basically disposable. So it's a single use only. So you cannot have cross contamination in this sensor. So because we are working with urine from the patient, you can reuse it, but because according to our research, we found out that it will cost more to clean it and sterilize it, for the next use. So we decided in this project that we're going to focus on a disposable unit. So you get the answer on that one. It's a one use only. The second question is also really good and really interesting also. Of course, you can use it for other bacteria or even proteins you can detect, because the only thing you have to do is to isolate your target cells. We did E. coli bacteria, but you can also, for example, isolate other type of bacteria, and you will just stamp these in these polymer layer, and then you will just create these cavities with the same geometry and dimensions of that type of specific bacteria you use on that stamp. So you can use it for a lot of different type of bacteria, and there have also been research on many other bacteria, even on cancer cells and tumors and also proteins. So that's quite interesting and fascinating. And in the future, this whole surface imprinted polymers will be a really big thing. But now it's just upcoming, because it's quite new technology. And I'm actually really confident also that these surface imprinted polymers will be a big player in the medical field. And so there you get the answer. It is possible to use it for other types of cells and bioparticles. Thank you for the question.
Thank you. Another good question from our audience. How do you ensure that the only cell bound on the SIP receptor is E. coli and not any other chemical content? Example, inorganic salt, protein providing a false result.
Another wonderful question. I really love these questions from this audience. Thank you. So that's really interesting. And we did also research on that, actually. So we did, of course, we have these little cavities on the surface layer of the polymer. And of course, there can fall in other particles, which are not our target cells, right? But the most important thing here is that when these other bioparticles fall in these cavities, and we also discovered in the research that when we flush away with a fixed flow rate, I cannot say the type of flow rate because it's confidential information, but we can flush it away with a fixed flow rate, and when we flush it away, these different bioparticles which are not suited for these cavities will flush away. But the target cells, which has these same dimensions and geometry, they will stick in these cavities. They will not flush away. So you will only flush away these particles which are not meant to be in the cavities. So they cannot bind to these cavities. When we flushing away with a fixed flow rate, and we also did a lot of research on that, and there are also been published many papers about it. So it's working basically.
Okay, great. Thank you so much, Oktay. All right, so we're going to wrap up the Q&A session now. Moving forward, I would just like to thank you again, Oktay, on your presentation, Preventing Antibiotics Misuse with HTM Sensor Technology. Thank you again to our judges for taking time for the questions, and our audience. Please, we encourage you to participate moving forward with any additional questions to our upcoming presenters. Thank you again, Oktay, for your time, and it's a pleasure having you here represent Europe.
Thank you for having me.
Okay, so that was our finalists for the Europe. Today, we would be moving forward to our third competitor for the Americas, Jeremy Lalchand. Jeremy is a mechanical engineer from Trinidad and Tobago with 8 years experience across varying industries, such as the oil and gas industry, manufacturing, and petrochemical. He is currently pursuing a master's in engineering asset management with a focus on improving reliability, maintenance planning, and scheduling systems. Today, his presentation will be an analysis of the maintenance and reliability of positive displacement diaphragm pumps.
Good day, everyone. My name is Jeremy Lalchand. I am from Trinidad, and I am here to present at the finals of the IMechE Speak Out for Engineering competition. I hope everyone is safe, and good luck to all participants. Today, I would like to present on a study I would have done while working on an ammonia process plant. The study is centered around the reliability assessment of two process diaphragm pumps that were known bad actors, meaning they were experiencing more failures that the plant team would have liked. This is a photo of a petrochemical plant similar to the one that I would have worked on. This is actually a methanol plant. My plant was next door, but for privacy reasons I am unable to share a photograph of my plant. A bit about my background. Since leaving university, I have worked primarily in the petrochemical industry. However, I will be moving on to oil and gas exploration in a few weeks. I have an undergraduate degree in mechanical engineering, and I'm currently pursuing a master's in engineering asset management. So to let you know all about this project. With respect to a career in mechanical engineering in Trinidad, the field is focused heavily on the maintenance of assets and improving reliability, as opposed to engineering design. This requires the collection of reliability data for analysis, which is then followed by recommendations for improvement, implementation of recommendations, and evaluating its effectiveness. It's not the most glamorous part of engineering, however, it adds significant value when looking at the overall operations and maintenance of petrochemical facilities. Reduction of maintenance costs by improving reliability results in better performing facilities, especially when considering the global challenges we face today. Before I get into the specifics of the study, I would just like to introduce the audience to the concept of a diaphragm pump. I have an illustration on the slideshow which shows you various technologies. A diaphragm pump is used to raise the pressure of a fluid. However, the difference with your pump at home and this pump is that this pump raises the pressure to a few thousand psi or pounds per square inch, while the pump at your home generates just about 40 to 60 psi. So this pump generates a lot of pressure. Let's look at the first two images. At the top, think of a syringe that is used in medical applications, but instead of a needle, there's a rubber flap. All right? Have a look at the last two images at the bottom to get a better idea. As the piston moves out, the diaphragm is pulled out, creating suction, just like a plunger that's used to unclog a toilet. And on the compression stroke, that's the compression stroke, the fluid is pushed and hence pumped. All right, so I'm just moving my cursor. You can see the diaphragm pump, this orange part here. This is the plunger. We have the suction stroke as it goes out, and the compression stroke. At the bottom is the suction. On the discharge here, you can see two check valves, one here and one here. All right, moving on. Importance of both pumps. If both pumps are ever down at any point in time, a sub-processing section of the plant has to be shut down, thus resulting in production losses which can range from 150 metric tons to 250 metric tons of ammonia per day. This translates to about 255,000 TT dollars or 40,000 US dollars. As you can see in the picture, there is one duty pump, the 131J, and one standby pump, the 131JA, which is always lined up and ready to be switched in case of an issue with the other during operation. Alright, so 131J is here and 131JA. Now, sometimes the 131JA may be the duty pump and the J may be the standby. So just keep that in mind. The normal switching period is every week, which means the pump has an operational uptime of about 6 months each year. A bit about the pumps again. They are of a triplex design. So you have 3 positive displacement pumps assembled with 3 crankcases. All right, these are the crankcases here, and driven by a motor and gearbox to form one complete unit. And the process fluid is water with ammonia. All right. So here we have another photo of the pump. We can see this is the motor across here, the gearbox, the crankcase, the pump heads where the pumping actually takes place, the dampener to reduce any vibrations. These type of pumps tend to generate quite a bit of vibration, which may result in piping failures. So the dampener reduces the likelihood of a piping failure. And we have a pressure reducing valve or pressure relieving valve should there be an overpressure condition. Moving on to another photo of the pump, we can see the discharge line here at the top. All right, there are 3 pump heads, as I would have mentioned before. Pump 1, 2, 3, which makes up one complete pump. This is where suction to the pump takes place. This is a check valve, here again and here again. A pressure gauge. As you can see, it's reading about 0, which means this pump is offline right now. And we have another pressure gauge here to identify or indicate when diaphragm has failed. All right. All right, some more illustrations of the pump, just to give you a better feel of this pump, right? As you can see in the first image, this illustration shows the main components of the system. We have the motor, gearbox, crankcase, and pump head. All right. A more detailed photograph of the crankcase. Now, the general principle of operation: the motor drives a gearbox, which is connected to a crankshaft, which is connected to 3 piston plungers, which operate in a reciprocating manner, similar to the pistons in a car, to pump fluid through the pump. All right, this is the pump head. This is the diaphragm here, check valve here, piston plunger. All right. So why would we have done this study? Naturally, one would ask, why? To put it simply, it is a known bad actor, and the company wanted to do an investigation to be done to analyze the performance and life cycle cost to date. All right. Some of the goals of this project included to quantify the expenditure incurred and analyze. Let's look at the overall life cycle cost, the mean time between failure, identify the most common issues with the pump and mean time between failures. The formula to calculate the MTBF is the operational time, which is how long it has been operating, divided by the number of failures. We also wanted to compile and analyze the history for defect elimination purposes, or root cause analysis. And most importantly, to make recommendations for improvement of reliability, maintenance, and critical spares stocking. All right. Some common known problems included high metal particle count in the crankcase oil, discolored oil in the pump head, failed diaphragms, which resulted in low flow or no flow from the pumps, failed check valves, the symptom being a loud knocking sound. You would hear it as you pass by the pumps, and the pulsation dampener, high vibration on discharge piping. All right. So what are some of the findings? So let's delve into the cost. The total maintenance cost was about $571,000 during the period 2011 to 2019. Breaking it down a bit further, we can see that the 131J would have incurred a cost of just over $300,000 in maintenance costs, whereas the 131JA just about $250,000. Just to put some things into perspective, an entire new pump costs around 1.5 million TT dollars, with an estimated 300,000 TT in spares and 600,000 to install. So therefore, a couple of new pumps for the plant would cost around 3 million TT dollars, or about $500,000 US dollars. Let's look at a breakdown of the cost in a bit more detail, right? So we have the 131J and we have the 131JA. The spare parts cost reflected about 89% of the total expenditure in maintaining the pump for the J, and for the JA it was around 90%. We can see the cost breakdown by maintenance costs that we would have engaged contractors for, and the cost for employees which are in-house, and the estimated maintenance downtime and equipment unavailability for this period was about 16 days in 8.5 years for the first pump, and just about 2 weeks again for the second pump. So now we have some perspective of where the money is being spent, and as you can see, the majority is in spare parts. From the Pareto charts, we can see that for both pumps, the bad actor sub-assemblies with the most downtime are the pump head and the crankcases, and as such, the rest of the presentation will focus on these two items. So the pump head and the crankcase, 15 failures, 10 failures for the J, and 25 failures and 13 failures for the JA. Alright, let's delve in a bit deeper. We are looking at the pump head across here for the J pump and the crankcase. Alright, from the sub-assembly level, we can see that the average MTBF, or mean time between failures, for the crankcase is about just under 4 months, and for the JA, it's about 5 months. We also see that the MTBF for the pump head is at about 2 months. For the JA, the MTBF stands at just about 3 months for the J. This tells us that there is a marginal difference in the mean time between failures for both pumps, so they're experiencing relatively the same MTBF, give or take a month. So let's look at cost again. Alright, take a closer look at the pump head. These charts illustrate the MTBF trends since 2011. There has been a general downward trend for both pumps, with the 131J experiencing a better MTBF in 2019, but there were 2 failures which occurred after the report was generated and were not accounted in these charts. There was a cutoff point. So what do we see here? The 131J has been experiencing an MTBF of around half of that of the JA in the last 5 years. That is, it's been failing at a rate of 2 times as much as the other pump. Alright, so we can see sometime after 2013 something would have changed, and the pumps are performing better. You can see here it plateaued. Relatively the same for both pumps. Alright, something would have changed, however, between 2013 and 2014. Looking at the crankcase, a similar trend compared to the pump head, with a MTBF for the JA being 2 times better than the J. The MTBF for the crankcase for the 131J is around 4 months for the last 5 years and 7 months for the JA. Considering the 4-month MTBF for the J, in reality the failure was being experienced on average around 3 times per year. The JA was just about 1 failure per year. Again, as you can see, they are relatively the same, and I will delve into this correlation a bit further in the presentation. Alright, now to discuss some of the challenges faced during the investigation and the gaps I would have highlighted in the way maintenance is being done currently on the system and at this facility. There is no real focus on root cause analysis, just repair the pumps after they have failed. No failure reports were generated. However, similar failures on other plants would have showed the gaskets on the inspection covers were a major issue, even though, well, the consequences were major, while the issue was very small. The pump head and the crankcase, they were the bad actor components or sub-assemblies within the entire pump. In the pump head and the crankcase, there was oil contamination, which would have led to downtime. Too much preventive maintenance was being done. The PM was being done almost every single month. So this is how it would have evolved. The pump would have failed and failed again and failed again, with the initial PM schedule being almost every 3 months. And because it was failing so often, they decided to reduce the PM interval, and this actually caused maintenance-induced errors to occur. All right, point number 7, failures induced by maintenance errors. And lastly, ineffective and improper use of the CMMS, or the Computerized Maintenance Management System, and not so much work order planning. Very little work order planning was being done. So what are some of the gaps I was able to identify? The first one, sometimes the work order for the 131JA was tagged to the J and all planning was done using this work order. The correct pump was determined in the investigation by reviewing close to 1,000 emails from the last 9 years. It was a really challenging task to go through all of these things. But looking at the investigation and analysis, we look at work order and life cycle planning. All right. The issue was reported and a work order was created. The issue was investigated, planning initiated, parts identified, job scheduled, job executed, and failure report generated. Some of the gaps and limitations included failures reported for the 131J, but work order was tagged to the other pump, and vice versa. All completed work orders reused in the future. No new work orders were created. Work order was used to issue parts that was not tagged to the 131J or J. And general PM work orders were not tagged to any specific equipment, so they just created a general parent work order and completed PMs on various pumps and not just the 131J and JA. Moving on, let's look at one of the work orders, do a bit of inventory analysis. So we have the work order number. This was the work order I would have pulled this data from. We can see there are all these parts and the stock numbers, the quantity that was issued, the cost in US dollars. We can see in April parts were issued from this work order, June, February. So this made it a bit more difficult to pull and analyze data. You had to look a bit more closely at each work order. All right. 3 different repairs were tagged to this one work order. The work order was used to repair a motor, but it may have been one that was replaced with a spare some time ago, but this work order was used to create a requisition. All right. More detailed analysis was required to determine how many work orders over the period were used this way, but luckily there were just a few. But this investigation highlighted the need for proper work order management. So what have we learned from this investigation? All right. There is a need for a review of the maintenance philosophy. All right, rethinking the way failures and maintenance of these pumps are viewed. A crankcase overhaul does not mean a pump head overhaul is required. You would find that every time there was a failure on the pump head, they would go into the crankcase and vice versa for the pump head. This just actually increased the overall cost for maintenance. All right. There is the need for root cause analysis and defect elimination. This just is not being done. The pumps are overhauled quickly and put back into service. Need for proper use of the computerized maintenance management system. A more robust planning, higher quality maintenance, and lessons learned. So what do we need to do? Conduct root cause analysis. train personnel in conducting root cause analysis. Make it part of the entire maintenance process. Develop failure reports, documenting the as found condition, that is before you actually start work on the equipment and replacing parts, right? Actually modify the gasket cover to accommodate the upgraded gasket, which would prevent contamination of the oil. Typically, you would find in periods when there's a significant amount of rain, the rain actually gets into the oil because the seal isn't working as it should. With respect to the PM program, revert to PM interval prior to 2013. Review future failures and adjust the PM interval based on findings and analysis. Conduct training and performing PMs. Several times oil ports were clogged by silicone gasket material. Silicone is used to seal the inspection cover to the pump itself, and while they use the scraper to scrape out the silicone, some would have fell into the oil sump, thus clogging oil ports and starving the unit for oil. Let's train personnel on the use of the CMMS and implement a full-time maintenance planner, especially when it comes to these pumps, considering the cost impact to the facility. Perform this exercise periodically, in that review the life cycle data for similar equipment. All right. Immediately, let's prioritize. Let's manage quality, right? Implementing mechanical completion checklist records, which is just a record certifying that the pump is good to use. Immediately, let's ensure each new issue is captured in an accurate work order on the CMMS. All right. And use only one work order to create the specific, use only the work order created for the specific issue to plan and add parts, including preventative maintenance work orders. Some work order etiquette will be nice. Keep the system clean, relevant data updated accordingly. Long-term recommendations. Configure the CMMS to allow for entering of asset management codes. These are failure codes. So if the problem was the bearing would have failed or a bearing failure, you use this code in the system. If there was an issue with the oil, you put that into the system. Any other type of failure codes that you can use. So when it's time to do root cause analysis, you have a lot more information to work with. And then train people on how to use this feature of asset management codes. Continuously review maintenance practices and lifecycle costs, and implement maintenance audits. So, pretty simple when you look at it at a high level view. It requires a lot of work and discipline by the maintenance team. All right. So, thank you. Just a little anecdote there. The greatest danger in times of turbulence is not the turbulence. It is to act with yesterday's logic. All right. Thank you very much. And have a good day.
Okay. Thank you, Jeremy Lalchand. That was Jeremy's presentation and analysis and the maintenance and reliability of positive displacement diaphragm pumps. And Jeremy will be representing the Americas today. We now like to open our Q&A session. Again, please, audience, if you have any questions, please feel free to drop them below in our chat box and we will address them to Jeremy. We will now begin with our judges. Terry?
Hello, Jeremy.
Hi, good day.
Hi. Great presentation. Really interesting subject as well. So thank you for delivering that. I've just got a couple of, well, it's kind of one question, but it might have two parts to it, really. So the question is really, when you set off on this project, had you set yourself some sort of targets for what you wanted to achieve? How much of a efficiency saving or cost saving you wanted to achieve? And then the second part of the question really is that having kind of come up with all these recommendations, and they all look like you've put a lot of work into to work out what they should be. Have you yet been able to quantify the effect of those recommendations? Have you got some results that show the improvement?
The first question. Sorry, could you repeat the first question? I didn't catch it.
Yeah. Sorry. Yeah. It was really just if you'd set yourself a target at the start, really, in terms of what you wanted to achieve in terms of cost saving.
Well, it was to determine whether we need to actually buy a new pump or invest more in the maintenance of the pump. I would have evaluated the cost of actually installing new pumps, and it was determined that it would have made more sense to actually buy new upgraded pumps and install it in the facility. The downtime being accumulated to repair the pumps is just too much. It was adding up to millions and millions of dollars over the years. So we just decided to go ahead and put through an order for an entirely new system. All right.
And the second part,
remind me,
really, have you seen the what sort of improvement have you seen?
Well, the team would have taken a closer look at the way they do preventative maintenance across the entire facility. In particular to these pumps, because of the actual figures they have now to look at when making maintenance decisions, you find that management has taken a closer view on do we really need to be replacing these parts? Do we have the actual competence in-house to do it? And just really pay more particular attention to what's going on. What they found was the technicians would take out parts from the warehouse and rebuild the pump, but there was no need to do all this work. Overtime was a big factor. The longer the repairs take, the more overtime you get. So it's things like this, changing the culture and the way you look at it. You want to shorten the mean time between maintenance effectively.
Okay, thank you, Jeremy. Thank you.
Hi, Jeremy. Nice to meet you. And thank you for a very good presentation. I'd be interested, it was a very detailed project you went through, very thorough. And I'd be interested to know that if one of your colleagues was running a similar project, what advice would you give them?
Pay attention to details. The devil is in the details. In my experience in a maintenance and reliability environment, there's a tendency to just overlook the minor details. We say the pump has been repaired, put it back in the service, and all is well. However, sometimes we fail to take into account that we can do better. When undergoing such a large task like this, break it up into several pieces and tackle each one and put your best effort into each discrete subsections of it, because there is a lot of value to be found and to be contributed by doing these type of studies. You should know that this is the fourth ammonia plant I would have worked on of this type, so the findings did not just impact the plant I was on, it impacted 3 other plants, resulting in millions of US dollars in savings each year. So just pay close attention to what is being done and work from there.
Thank you, Jeremy.
Hi, Jeremy. Well done. That was very informative, and I can tell that you've had to do a lot of research because it had a lot of detail and technical information. So my question is, what made you choose this project, and why did you find it interesting?
Well, the job I actually had was to do an analysis of the plant that I was working on all equipment, all rotating equipment, pumps. This isn't a rotating piece of equipment, but there were rotating components such as the gearbox and the crankcase and the motor. So I was doing a inventory analysis by looking at the mean time between failures for each turbine, pump, compressor. And this pump was identified by the management of the company as a particularly poorly performing piece of equipment, and they really wanted to get some perspective on what we can do better. And because this was my fourth ammonia plant, fourth experience in working with these pumps, me to analysis for the company. So it's because of my experience working with these pumps, and the need of the company to do better and to better understand the performance and the cost being incurred. They asked me to perform the study.
Great.
I would have actually used this project as well for one of my courses in my master's program. It just so occurred that everything lined up at the same time. So after I would have
Yeah.
done it for the company, I was able to print it at school as well.
Oh, perfect. Cool. Thank you.
Jeremy, that was a very detailed presentation that you did. Congratulations. I don't have any questions for you today. Thank you.
Thank you.
Thank you, Stephen. Thank you, judges. We now will open the question and answer segment to our audience. Are there any questions that the audience may have? Please feel free to drop them below. We do encourage your questions as, again, our participants are being judged on how they respond to your questions. So it's all part of the competition. You're participating, and we do encourage those questions. You're helping us as well, and you're involved. So if there are any questions, please feel free to drop them across. We are open to them.
So Samantha, I can come back with another question I was holding back, if you like, just to
Of
give
course,
people a chance.
definitely. Thank you so much,
Jeremy,
Terry. Sure.
a lot of what you're doing relates to the quality approach to the process, and I'm just wondering what kind of quality systems you operate at the plant, and were you recommending any changes to the quality process or the quality systems that you have there?
On this particular plant, there is no formalized quality system such as the ISO 9001 2005. One of the plants I would have worked on previously, they had a system in place. So when I joined this new company, I was able to migrate some of the philosophy to the company. There is need for a quality management system at the company, and it was a recommendation. So it has to be implemented. I would have moved on from this company since then.
Yeah. Good. All right, Jeremy, thank you. Thank you very much.
We have a question. Thank you, Terry. Thank you, Jeremy. We do have a question from the audience. Hi, Jeremy. From your data, it seems like one of the major factor for ineffective PM is due to human errors. Did you consider weighing in human errors?
Yes, human errors were found to be one of the leading causes of maintenance-induced errors. In particular, the gasket material. Basically, you have a cover sitting on a plate, and when you remove the cover, there is silicone, and when you scrape it out with a scraper similar to a paint scraper, you find little pieces entering the oil port and clogs it up, so you stop the unit for oil. Other issues that you probably wouldn't know just by looking at it, but doing further in-depth analysis of the type of failures. The wrong type of grease has been used on some of the bearings. The motor fan was broken in one instance, leading to overheating of the motor, just because of poor handling of the unit, using the improper equipment to move the motor. So it was a factor. When I looked at, so I would have stood there at the job site looking at the way technicians have been executing the preventative maintenance, just looking at their general housekeeping and the way you perform the job, and compared it to my experience. Because as a graduate training engineer, I would have worked on these pumps at other facilities with a more developed team. So just by when you look at someone doing something and they know what they are doing, and they're doing it right and to the best of their ability, or to the highest standard, you can see it up front. So it's not that the team was an ineffective team, it's just that they needed a bit more training and experience and exposure. So one of the recommendations that came out also was when they are doing overhauls on other facilities, you rotate the workers so they get that experience on this equipment, but on several other types of equipment, because they're basically rubber stamps of each.
Okay, thank you, Jeremy. We do have one more question as well, and it's a two-part question. So preventative maintenance is meant to preempt any possible failure. Having too many preventative maintenance could be an indication that there is some problem inherent and there is some undetected, and probably there's not enough to have a more thorough inspection to detect the problem. If you agree with this, then the second question is, how frequent do you consider as not too many for preventative maintenance as compared to monthly preventive maintenance? Did you
Well,
get
that's a
that,
very
or would
good
you like me
question.
to? Okay.
That's an interesting question. I was actually asked this question. Well, I would have asked this question during my study why it is they would have changed the PM interval.
Okay.
Typically, in generating an interval for preventative maintenance, you would like to look at condition monitoring data, such as vibration, temperature, level analysis. And these condition monitoring parameters will assist you in evaluating the condition or the amount of degradation that's taking place over time. And you look at the trends over, let's say, a year, and you establish, hey, every 6 months we notice that we're getting a bit more cuttings in the oil. Let's shorten the gap in which we do the oil analysis because we don't want the deterioration to reach to the certain point. So you use condition monitoring data to guide you as to how soon a failure may occur or how badly the deterioration is taking place. All right, and what I found was that the 1 month interval, there was no real basis behind it other than the fact that, hey, someone in management would have said, this pump has been failing too many times, let's shorten the PM interval. That was it, and it went on from that point on for years with 1 month intervals and preventative maintenance. When the proper way of reevaluating the system is using condition monitoring. What I would have also found is the type of condition monitoring being done, they were using the wrong type of transducer for vibration analysis. So it was not giving you the right spectrum or signature of the vibration. Because it is a reciprocating system, the transducer has to be able to pick up the specific frequencies. You found out it has been heavily influenced by the crankies and constant pulsations and skewing the actual results that you're getting. So they're showing there were more problems when it really wasn't much. External noise basically on the frequency.
Well, thank you
So
for your
one
time,
of the
Jeremy, and
recommendations
thank
would
you.
be
Okay. Okay. All right. So thank you, Jeremy. Thank you for representing the Americas and your presentation and analysis of the maintenance and reliability of positive displacement diaphragm pumps. Thank you again to our judges. We will now like to move forward to our final competitor for today. And our final competitor for today is from the UK. We have Callum Wilson. Callum Wilson is a PhD student at the University of Strathclyde and is part of the ICELab research group within the Aerospace Center of Excellence. His research topic is intelligent control for onboard spacecraft control with a focus on reinforcement learning techniques. Today, we will be viewing his presentation, Artificial Intelligence in Engineering.
Hello, my name is Callum Wilson, and this is my presentation for the IMechE Speak Out for Engineering World Final 2020. This presentation is titled Artificial Intelligence, or AI, in Engineering, Demystifying the Black Box. The contents of the presentation are as shown. First, I'll give an introduction to AI broadly, and then talk about its application in engineering. I'll then discuss some views of AI from the general public, engineers, and AI researchers. From this, we will see some issues emerge, which I'll discuss in the next section, and the so-called black box approach to AI. And following this, I'll present a different, better approach to using AI in engineering. Finally, I will present some conclusions. So to start with, an introduction to AI. When most people think of AI, it conjures up images of robots and super intelligent machines, which comes mainly from films and perhaps other popular media about AI. But what actually is AI, and how can we use it in engineering? Well, the definition I'll give here, based on certain other definitions available online, is that artificial intelligence is a machine which solves problems in a manner that mimics human intelligence. Now, this definition has its own problem of having to then define human intelligence, but instead we can think of artificial intelligence as knowledge-based systems, evolutionary algorithms, and there are many more examples. So how can we use this to solve engineering problems? Well, the applications of AI in engineering, the most common ones, are for optimization, where we want to maximize or minimize a certain characteristic of a system. Autonomy, where we have vehicles or machines that operate in environments that are difficult for humans to intervene, such as for a Mars rover. Dealing with uncertainty, a very inherent characteristic of most real-world problems that AI systems are good at coping with. Knowledge extraction, so in the vast corpus of readable data that we have, AI is able to extract useful information from these. And finally, as an example, for complexity, when problems get too complex for traditional methods to solve, then we can use intelligent methods instead. So now on to views of AI. As I said before, when most people think of AI, their opinion of it comes from films and media, and so quite often we start to think of apocalyptic scenarios with machines becoming more intelligent than us. Obviously, this is not entirely grounded in reality of what AI does currently, but it's still worth thinking about how you feel about AI. Do you see promise in it? Do you think it is completely overhyped and is actually not really very useful? So first, talking about the view of the general public. Now, first we have an analysis which looked at how different articles that discussed AI perceived it, whether the overwhelming tone of the article was positive or negative. So the first thing we can see is there was a sharp uptick in discussion following 2009, which makes sense because AI is becoming ever more popular. And also the tone of the articles was overall optimistic. So this surprised me somewhat that most articles discussing AI tend to be optimistic about it. Now, looking at another survey, this looked at members of the general public and how they understand or perceive AI. So of the survey respondents, the vast majority, 75%, did at least have some idea of what AI is. Only 14% believed that they'd had direct contact with AI. The actual figure is likely to be a lot higher than that because many of the apps that we use very often today incorporate AI to some extent. And finally, only 2% of the survey respondents thought that AI is already having an effect on society. And now, while the magnitude of the effect can be up for debate, I think it's quite clear that AI is already having some profound effects on society. And so the conclusion says that the public understanding is perhaps broad, but not very deep. So what about engineers? Well, if we look at the IMechE news and have a look at some headlines which talk about AI, we can see that overall, again, these tend to be very optimistic. They talk about things like how it can help the hunt for new materials or identify alternatives to liquid batteries. So here, AI is really being shown as a useful tool that can expand engineers' capabilities. However, there is also clearly a knowledge gap currently among engineers, and this is best shown in this response from Dr. Jennifer Baxter to a House of Lords report. So she says that this shows that retraining is going to become a lifelong necessity for people to keep up with the changing job requirements as a result of AI, and also that it is very important for engineers to understand how AI can be used. So reading between the lines here, it seems that currently engineers perhaps do not understand how AI can be used as well as they should. And now finally, AI researchers. Now obviously I can't speak for all AI researchers, however, looking at one specific aspect of AI that's frequently discussed these days, that is explainability. And modern state-of-the-art AI systems often lack this characteristic. So what that means, as this quote shows, is that the way they get to their decisions, though their decisions may be very good, is highly non-transparent. And this can be a problem for certain safety critical applications. As an example of this, here is a common structure in state-of-the-art systems called a convolutional neural network, where we have some state input, usually a vector of numbers, and then we have some output, which could be a decision or a classification. In these first layers, we have these so-called convolutional layers, which have a kernel function that goes and does some linear algebra along each of the elements of the input, so a bunch of maths going into it. Then after the convolutional layers, we might have a neural network, which has these artificial neurons that calculate more maths with the inputs, and then eventually it spits out a number at the end. This is the overall structure, and as you can probably see, this doesn't really represent reasoning in a very human way. It's not very easy to see how a system like this actually came to reach its output. And so, generalizing very broadly across these three groups of people, I think there is one common theme among all of them, which is this: nobody has any idea how it works. Now obviously this isn't strictly speaking true. It would perhaps be more correct to say that AI researchers don't exactly know how it works or why it works. Engineers have a lack of general understanding of AI, and the general public perhaps don't know that AI works at all and might be oblivious to it. But obviously this can present some problems. So now I want you to imagine a black box. This black box is a perfect predictor that can predict anything you ask it. It could predict whether it's going to rain where you are. In fact, more than that, it can predict the exact start and end time and the exact number of raindrops that will fall in this time. So you're able to get predictions out of it, but you are unable to see how it reaches those predictions. Now let's say it predicted who your future life partner is going to be. Or perhaps you used it a year ago and it predicted all the events of 2020. Perhaps you'd be starting to wonder then, how does it reach these decisions? How does it know this? But you're not able to find that out because it's just a black box that you can't see inside. Now, this is a way that people often treat AI problems. AI is seen as this black box into which you feed a problem, and to solve that problem you just give it data, the more the better. And then out of that we will get a solution. It might not be the right solution, but if it isn't, then we just retrain and keep going until we get a solution that looks like it might be correct. So as a trivial example of this, perhaps we are wanting to determine if a picture is of a cat. So what we will do is we will show it a picture of what we want to know if it's a cat, and we will train it on lots of pictures of cats and not cats to distinguish between them. Now in this case it's correctly identified that yes, this is a picture of a cat, but perhaps we can fool it. We show it this picture, which is obviously a person in a cat mask, and then it outputs that yes, this is a cat, when in fact we can clearly see that this is wrong. Similarly, if we showed it a picture of a hairless Sphinx cat, then it might say that no, this isn't a cat, even though it is. And perhaps we would see fit to retrain it again, but obviously we're never going to be able to perfectly capture every single possible edge case. Now, in this toy example, obviously it's quite harmless and we can sort of laugh at the machine when it gets it wrong, but what if we took this approach in a real world problem? Well, a good example of this is the Amazon recruitment assistant. This was some research they were doing a few years ago into automating the recruiting process. Obviously, scanning through CVs and reviewing every application is quite a lengthy process. So ideally, what they wanted, as I said here, is a machine into which you can just feed a bunch of applications and get out, these are the best candidates. However, they had to scrap it because they found that it showed a bias against women. In fact, if there were any words relating to women on a CV, for example, women's college, it would downgrade that CV. Now, this is because it was trained on previous recruitment decisions, and those recruitment decisions had human biases in them from the humans. Now, quite often we're prone to thinking, but AI is not racist, sexist, biased. However, this shows that that is not true. The AI is as biased as the humans and the data generated to train it. So this is what happens in the real world if you take a problem and you just feed it lots of data to try and reach a solution. It might show interesting and perhaps harmful behaviours to get that solution. So how can we do this better? Well, as an example, I'm going to refer to a Kaggle competition about faulty steel plates. So Kaggle is an online community of data scientists that regularly holds competitions where people will make public some data that they have for a problem, and some of the best machine learning scientists in the world will try and solve it using a variety of means. Now, in this example, the data set is of data to do with steel plates, and these all have different types of faults. So one way of approaching this would be the black box approach, as I show here. We feed it all the data that we have that is labelled, and we say, can you classify these faults, and we will get a string of numbers out. And we might keep doing this again until the string of numbers starts looking like what we want it to be. But this doesn't really tell us very much about the problem, and is very difficult to fix if things are going wrong. However, if we look at some of the notebooks that were submitted to solve this problem, we can see that there is actually a lot of rich information that we can extract from this and visualize, which is very useful, much more useful to show people. For example, we can look at the imbalance in the data set for the different faults, which would suggest that we need to try and do some class balancing to make sure the data set isn't biased towards just one class. We can look at the feature relevance, which tells us which of the inputs to the system are most useful in reaching a decision, and that can help humans learn more about the problem as well. And furthermore, we can see that when it's making mistakes, when it's classifying as the wrong fault, if we look at this confusion matrix, we can start to get an idea of which faults it is not distinguishing between very well. So by not just taking a problem and shoving it in an AI black box, we can actually generate a really good wealth of information about a problem that can be incredibly useful to engineers. In conclusion, we have seen that AI is a really useful tool for solving a wide variety of engineering problems. While the debate used to be as to whether we should allow AI to be used in engineering, it is clear that the use of AI in a wide variety of engineering applications is now inevitable. And this is a good thing, because it will help us solve some of the toughest problems we face now, such as climate change. However, we aren't going to solve climate change like this using a black box, if only we could do it so simply. However, what we can use AI for is to improve our climate models such that we can understand how the climate is changing, accelerate societal adaptation to the necessary lifestyle changes, and also reduce emissions from electricity by optimizing the generation and distribution on grids. However, this will only be possible if we have engineers who understand how to use AI.
Hi, Callum Wilson. Thank you so much for your presentation. And again, thank you for representing the UK with your presentation, Artificial Intelligence in Engineering. We are now about to open our Q&A session with our judges and, of course, the audience. Thank you again, audience, for your questions. Please feel free to leave them below, and we will be directing them to Callum as we proceed. So, judges, Terry.
Yes, thank you, Samantha, and hello, Callum.
Hi there.
Hi. So, Callum, great presentation. I love AI. I absolutely love it. I'm from an automotive background, so you can see perhaps why I like it so much. But you picked up on a really good example, I thought, about the diversity that was being identified incorrectly in the CV scanner. And that's a really good example. But if you take that to a slightly different level, you start thinking about ethics. And if you want AI systems to be widely accepted by the public, how can we manage the ethics, and who's going to actually decide, and who's going to verify and say that an application is acceptable when it comes down to some really fundamental things like the ethics of the decisions that the box makes?
Yeah, that's an excellent question, and something that's perhaps not being discussed enough at the moment. This is definitely a field where regulation is catching up with the technology, and it's probably the case that it's not widely regulated enough how we're using these kinds of technologies. For ethics, I think it's very important to have independent boards that are set up to verify the ethics. And I think also it's important that if we're submitting proposals for these kinds of technologies to funding bodies or whoever, there should be independent verification of the ethics, as well as, of course, within any company, they should be absolutely making sure to certify these internally. But yeah, I think independent boards that are set up purely for the purpose of assessing AI ethics really would be the way forward for that.
Okay, thanks, Callum. And would you see that actually becoming like a product liability issue, perhaps?
Possibly, yeah. I mean, this is a discussion that happens a lot as well with who's to blame when things go wrong. And I think it needs to be well documented, the development processes of these, because again, like I said, people are inclined to thinking, oh, the machine should be somewhat impartial, but it is endowed with all the biases and things that the designer puts into it. And so there should always be a paper trail of who's been working on a certain thing. And so when things go wrong, it can be identified why it went wrong and who was involved in that, as with pretty much any engineering project.
Right, okay. Thanks, Callum. Good answers. Over to Joanna.
Thanks.
Thanks, Callum. Nice to meet you. And this is a really interesting subject, especially for a non-engineer. I've spent I've been to a number of webinars and sessions with fellow colleagues on this subject, and I think it feels like the engineering community is convinced by it, but as a sort of non-engineer, I'm a bit more hesitant. And one of the reasons I'm hesitant, Callum, is because it's really complex. And even the term artificial intelligence, I'm sort of, well, what does that mean exactly? Which you've kindly explained today. But how do you think, therefore, perhaps it could be better explained or understood by the public to help the cause?
Yeah, that's another great question, because I think it's another one of these technologies that has so much hype, and it's amazing. Even though so many people have heard of it, it's really hard to get a concrete definition of what it actually is, even from within the community. So I think one way we could get more trust is to start thinking of it differently. And rather than thinking of AI as this inherently different and sort of super intelligent mechanism that is a bit far-fetched, we can think of it more concretely as a set of methods and a set of tools. And therefore it becomes like many other things in engineering that we use, for example, finite element analysis. It's just another set of mathematical tools that we can use. And that should be communicated, because at the moment when we think of AI, most people think of much higher levels of intelligence than what is realistically being researched and used at the moment. And so we're not developing, well, some people are trying to develop sentient robots, and they're probably a little bit off that at the moment, but that's not what is being regularly used. This is not, some people say all it is just statistics, but with a fancier name to market it better. It's maybe a bit more sophisticated than that, but yes, fundamentally, these are algorithms that use statistical methods. And once you start thinking of it like that, I think it becomes a bit more palatable.
Thank you.
Hi, Callum. That was really interesting. I'm a fellow engineer. I love technology and artificial intelligence. So, what I would like to know, what's your favorite piece of artificial intelligence technology so far?
Oh, that's an excellent question. So I'd be biased towards my own area of research, which is in reinforcement learning for optimal control problems and applied spacecraft. So AlphaGo is probably, I mean, that's one that a lot of people know, but for the benefit of anyone who isn't aware, AlphaGo was a program that was designed to play the game of Go, and it was able to beat the #1 player in the world. And the thing I found so interesting about that was that it taught the humans aspects about the game. And this was a game that, you know, chess got beaten by machines about 20 odd years ago, but they thought Go was going to be impossible. It was never going to happen just because of the level of complexity. But people looking at the way that this machine played, people actually got some insights from that. And so I think that was incredibly exciting. The fact that AI is now able to, we've got a sort of two-way feedback where humans create AI that's capable of doing great things, and the AI is then capable of teaching things to humans as well. So that's one of them. But if I could offer a second that I just really like to play about with, it's the concept of neural style transfer. And this is a popular one that people can easily do themselves as well. If you look it up online, it's basically taking the style of an image and transferring it to another image. And so you can make a sort of Van Gogh style portrait of yourself if you want, and things like that. And it really does look incredible. So yeah, creative AI is something I think is really interesting. I'll try to curtail my answer there because I could talk for ages, but yeah.
Those are really good choices, and those were really good explanations as well. Thank you.
Cheers.
Hi, Callum. Okay, I'm not an engineer, but I would like to ask a very general question. In your research, which engineering industry has shown good success in AI?
Okay, yeah, that's a good question, and I think coming back to what Terry said at the start with automotive, this is probably the one that people are most visibly seeing the real world applications of. And so autonomous vehicles obviously need to incorporate some amount of AI. And while it's still not perfect, obviously, we're already seeing that autonomous vehicles are capable of being safer than humans. So that's quite an interesting one. And probably where AI has been most used is on places like social media and Google. And I'm reluctant to call them a success because of some of the negative fallout that's happened. And obviously you can read plenty about that. But however, they have used AI. That's perhaps a good indication of what happens when you allow widespread application of AI to half of the human population and try and maximize clicks. We've all seen and heard what's happened because of that. So yeah, autonomous vehicles are perhaps one of the most interesting one, and image processing as well. I think image processing across that applies to a lot of fields, but that's seen great advantages. And yeah, there's a lot of really interesting uses of AI for that as well.
Thank you. Very good. Thank you.
Cheers.
Thank you to our judges. Thank you, Callum. We now have some questions from our audience. Our first question, Stephen Hawking called for the AI technology to be controlled to prevent it from destroying the human race. In your opinion, would you agree to have AI technology be controlled? If yes, to what extent?
Yeah, another good question. I think AI research should be controlled because at the moment we're heading towards this point of what people like to call the singularity, where what if you do create something that's more intelligent than humans? And as one of the founding fathers of AI, Alan Turing said, you just got to hope that you can turn it off quickly enough, really. And so, yeah, ideally, I would like the research of AI to be very controlled. I would like there to be monitoring as to where AI is actually being used and what it's being used for. That's very important. As for it taking over the world and destroying humans, you'd need to endow an AI with the ability to do that. And so, again, I would like to ensure that AI researchers are not endowing their systems with the ability to take over the entire world. But yeah, I think certainly some oversight is very necessary. And like I said before, regulation as well.
Okay, thank you, Callum. And we have a non-engineering question, which is from a financial perspective. If money was not a problem, how far can you take this work?
Yeah. So I think, interestingly, at the moment, with big tech and everything, to some extent, money isn't a problem for some of the research that's going on. What is a problem, what's becoming more of a problem, is actually the laws of physics and compute power. AI systems are quite often very data hungry and therefore very power hungry. And sure, with a certain amount of money, you can still increase the power, but we are reaching limits of how powerful these things can be. So an interesting recent example is the language model GPT-3 that has these billions of parameters that need to be stored. And so you really need to run it on a cluster of computers. But all that was an experiment in saying, okay, we have these types of language models that we've been using. What if we just make them a lot bigger? And they still seem to be getting better accuracy by certain measures. So I would say, yeah, perhaps if we equate money to being compute, we can keep making the systems that we have at the moment just bigger, and they, to some extent, get a certain degree of better accuracy. As for what specific problems that would solve, I'm less sure, because some of the most interesting applications of AI at the moment use very fundamental and not necessarily that compute-heavy algorithms. But certainly in the context of language modeling and things like that, and other things as well, probably autonomous vehicles, if you were just able to develop much more compute for it, there would be potential for them to be faster and to some extent safer and more accurate.
Okay, thank you, Callum. We don't have any more questions from the audience. Are there anything else the judges may want to ask? Or okay, great. Well, thank you so much, so much, Caleb. That was our UK contestant, Caleb Wilson, who just presented on artificial intelligence in engineering. Thank you so much for your time and lovely presentation. Thank you again to our judges and our audience for your questions.
Thank you.
Thank you.
Thank you again, Caleb. Okay, so thank you again all to our competitors today. This has been a fantastic day one of our competition. Thank you again to our attendees. Thank you so much for asking all of your questions. We do encourage them tomorrow, and we really do hope you had an excellent time. The competition continues tomorrow at 10 GMT. Please use the same link that you did to join today for tomorrow's session. Please be reminded that the session tomorrow, after the final 4 competitors have competed, this will culminate in the awards ceremony. We do hope to see you all tomorrow, and thank you again for joining us today. Good night. Good